Welcome to the video lecture EE-371 Electromagnetic Field Theory. This is Dr. Husnul Maab. In last lectures we have discussed current densities. We have also developed the continuity relation, and then we have discussed the three different types of material using the concept of conductivity and band gap theory. After that we have developed the conductivity relation for conductor and resistance. We can also use those relation for other materials instead of conductors too. Then we have discussed the property of conductors. As in conductor there are a large number of free charges. In the presence of applied electric field, all the charges come across the surfaces of the conductor, and then the surfaces of the conductor behave like equipotential surfaces. Then we have developed the relation for normal and tangential boundary condition of a perfect conductor. In this lecture you will learn that how to apply the image theory to define the potential difference and electrostatic field due to a number of charges or a single charge above any infinite plane. Then you will learn that the properties of semiconductors or semiconductors. Then how to define the Gauss's law in terms of free charges for dielectric materials. You will also learn the tangential and non-boundary condition at the boundary between two different dielectric materials. Let us first discuss the method of image. So in last lecture we have discussed the electric dipole. An electric dipole is basically comprises of two charges having same magnitude but opposite sign and separated by a small distance d. Midway between the two charges there is an infinite plane having zero potential. In figure B, the field configuration due to electric dipole is shown. In this figure we can replace the negative charge and the zero potential plane by locating an infinite conducting sheet of negligible thickness and positive charge. So this configuration doesn't affect the field configuration due to positive charge located above the conducting sheet. Let us see this problem in reverse direction. For example, we have given a point charge above the conducting sheet. So then we can replace the conducting sheet by locating the negative charge below the plane having zero potential at a symmetrical position, as the positive charge is located above the infinite plane having zero potential. This negative charge represents the image of original charge, or this is also known as the image of the original charge. So for example, we have given a large number of charge configuration above the conducting sheet. Then is it possible to apply this procedure to those charge configuration located above the conducting sheet? So the answer to this question is yes. By virtue of linearity we can apply this procedure to any charge configuration above the conducting sheet. So let us consider different types of charges located above the conducting sheet. For example, in this in the figure, we have a line charge, a point charge that is minus 4 coulomb, and another point charge which is located at another position above the conducting sheet having 1 coulomb value. So remove the conducting sheet by an infinite plane and the images of the above charges. So you can apply this procedure to any number of charge configuration. As in this example or figure, we have different types of charges, point charges and line charges, and we can replace the conducting sheet by locating the images of these charges below the infinite plane having zero potential. So the image theory is basically applied to any radiating structure which is located above the Earth's surface. So when any radiating structure is located above the surface, so we remove the Earth's surface by locating the image of that radiating structure, and that way it is very easy to define the potential due to that radiating structure or the electric field due to that radiating structure. You can apply the image theory, that is to replace any conducting sheet by locating the image of a charge, that is whether for example positive charge is located above the conducting sheet, then you can replace the conducting sheet of negligible thickness by locating the negative charge below the conducting sheet at a symmetrical position as the positive charge is located above the conducting sheet. Or you can replace the conducting sheet if for instance a negative charge is located above or below the conducting sheet, then you can locate a positive charge as the image of the given charge which is located below or above the conducting sheet. This is known as image theory. That is, in image theory, what we do, we replace a conducting sheet by locating a negative charge below an infinite plane having zero potential at a symmetrical position, as the original charge is located above the infinite plane. This is known as image theory. So let us apply this theory to a drill problem D5.6 on page 126. In this problem, we have asked that a perfectly conducting plane is located in free space at x equal to 4, and a uniform infinite line charge of 40 nanocoulomb per meter lies along the line x equal to 6, y equal to 3. Let V equal to, that is potential difference, is equal to 0 at a conducting plane at this location. At P, find the potential and the electric field at P point having coordinates 7, -1 and 5. So look at the figure. In this problem, we have given a line charge having line charge density 40 nanocoulomb per meter. The line charge is located at x equal to 6, y equal to 3 and z equal to 5. And the conducting sheet having zero potential is located at x equal to 4, y equal to 3 and z equal to 5. and x equal to 0 is located at y equal to 3 and z equal to 5. So let us apply the image theory to this problem and to define the potential and electric field due to the line charges. So then the configuration of charges look like this, as shown in the figure. The positive line charge density is located at x equal to 6, and the plane having 0 potential is located at x equal to 4. So the difference between the location of line charge and the infinite line plane is 2. So we have to look at the image of this charge at a symmetrical position below the infinite plane having 0 potential. So that position location occur at x equal to 2. So the difference between the plane location and the image of the line charge is 2 when we look at the negative line charge at x equal to 2. So this location actually represents the symmetrical position of the line charge, or the original line charge. The original line charge is located at x equal to 6, y equal to 3, z equal to 5, and the image charge is then located at x equal to 2, y equal to 3, and z equal to 5. And image charge, the line charge density becomes minus 40 nanocoulomb per meter. And now we have no conducting sheet or conducting plane at x equal to 4. The vector from the positive line charge density is denoted by a plus vector. The vector from the infinite plane having 0 potential to the field point is represented by b vector, and the vector from the image line charge density at x equal to 2 is represented by a subnegative to the p point. Let us first measure the magnitude of b vector, which is equal to 5. The magnitude of a plus vector, that is a vector from a line charge to the field point p, which is equal to square root 17. The magnitude of vector from image charge to the field point is becomes equal to square root 41. As the potential difference due to a line charge is given by this relation, that is V equal to rho L. Rho sub L represent the line charge density divided by 2 pi epsilon naught ln B by A, and the charge configuration is basically given in free space, so we will use epsilon naught in this relation. Now for positive line charge density, the potential at P point becomes equal to 40 into 10 power minus 9 divided by 2 pi epsilon naught ln 5 by square root 17. The potential due to a negative line charge density, that is the image charge at P point, becomes equal to this much. Now at P point 7, minus 1 and 5, the total potential due to the original charge and the image charge is basically the sum of the potential due to two line charges, that is V sub plus represent the potential due to positive line charge density, and the negative potential or V sub negative represent the potential due to negative line charge density. plug in the values of V plus and V negative in this relation, we come across this one. And as we know that when the argument of ln is in division, that is ln b by a, so we can expand this as lb minus la. Using this relation, we can divide the argument of the first log by the argument of second log, so which result in ln 41 divided by 17 square root. Remove the square root and bring that square root values 1 upon 2 to the magnitude of the multiply that with the magnitude of the potential, so it becomes equal to V equal to 10 into 10 power minus 9 divided by pi n to 8.854 into 10 power minus 12, which is the value of free space permittivity, ln 41 divided by 17. Using calculator, we obtained this value, that is V equal to 316.51 volt, which is exactly match with the answer given in the book. Now let us define the electric field due to these two line charges at P point. The coordinate of P point are 7, minus 1 and 5. So the vector from the line charge having positive line charge density is equal to ax plus 4ay. Using the coordinate of line charge and the field point, we obtain this vector, and similarly using the coordinate of image charge, line charge and the field point, we obtain a minus vector. On the right side, a plus k represent the unit vector directed along the a plus vector, which is obtained by dividing this vector by the magnitude of a plus vector, and the unit vector in the direction of a minus vector is obtained by dividing the a minus vector by the magnitude of a minus vector. As we know that the electric field due to a line charge is given by a relation which is highlighted in green color, that is rho L divided by 2 pi epsilon naught rho a rho unit vector. The unit of electrostatic field is volt per meter. The electric field due to individual charges, that is due to positive line charge density, is equal to this much, and the electrostatic field due to a line charge or image charge is equal to this much. Now by virtue of linearity, we can sum up these two fields due to both line charges, that is positive line charge and the image charge, which is equal to 40 into 10 power minus 9 divided by 2 pi epsilon naught. The unit vector, the vector directed along from the positive line charge density to the field point divided by magnitude of the vector minus 5ax plus 4ay. This represent a vector directed from line charge density having negative line charge density divided by magnitude of the vector. But actually in evaluating the electric field, the magnitude of the vector a plus multiply with each other in denominator, so that's why the square root remove, that is 17 and 41. After some numerical manipulation, we come across this result. This represents the value of electric field at P point. The electric field has two components, one along negative x-axis and another along positive y-axis. So far we have discussed the conductor properties. In conductor, the current carrier is electron, but in a semiconductor the current carriers are holes and electrons. The holes and electrons move in opposite direction to each other but constitute a unidirectional current. In the preceding lectures, we will discuss semiconductors and compare the property of this material with the property of conductor using the concept of conductivity. Then we will develop the theory for dielectric material. So in conductor, the current carrier is only electron. So in last lecture we have obtained the relation of conductivity for the conductor, which is equal to minus mu e. Mu e represent the mobility of electron, rho e represent the concentration of electron. The unit of conductivity is Siemens per meter or mho per meter, the reciprocal of the unit of resistivity. In semiconductor, the current carriers are electrons and holes, and the conductivity depends on the concentration of the two particles, that is rho e and rho h, and also the conductivity also depends on the mobility of the two particles, electron mobility and hole mobility. The values of mobilities and the concentration of charge and holes at 300 Kelvin for pure or intrinsic semiconductor, that is silicon and germanium are tabulated. That is the mobility of pure silicon at 300 Kelvin is equal to 0.12 square meter per volt second. The mobility of holes at 300 Kelvin for pure or intrinsic silicon is 0.025 square meter per volt second, and the electron concentration is minus 0.0024 coulomb per cubic meter. That of the hole concentration is 0.0024 coulomb per cubic meter. Per germanium at per pure germanium at 300 Kelvin, the electron mobility is 0.36 square meter per volt second, and the hole mobility is 0.17 square meter per volt second. The electron concentration at 300 Kelvin in pure germanium is minus 3.0 coulomb per cubic meter. The hole concentration is 3.0 coulomb per cubic meter. Let us note that in conductor, when the temperature is very high, so mobility is very low, and the electron concentration is also low. Hence the conductivity is very low, nearly equal to 0, and the resistivity is infinite. Compare this property of conductor to semiconductor. So in semiconductor or semiconductor at high temperature, the mobility of electrons and holes are very low, and the concentration of electron and holes are very high as compared to the concentration of electron at very high temperature in conductors. So hence the conductivity value in semiconductor at very high temperature is very high. Hence the resistivity is nearly equal to 0. So from this discussion we conclude that in semiconductors the conductivity actually depends on 4 parameters: mobility of electrons, mobility of holes, electron concentration, hole concentration. Let us try drill problem D5.7 on page 127 of the book. In this problem we have given using the values given in this section for electron and hole mobilities in silicon at 300 Kelvin, and assuming hole and electron charge densities are 0.029 coulomb per cubic meter and minus 0.0029 coulomb per cubic meter per electron. This one is for positive value of charge density represent for hole, and negative value of charge density represent the electron concentration. In part A we have asked to find the component of conductivity of silicon due to holes. So we have given all these information at 300 Kelvin. So the component of conductivity due to hole equal to mobility of hole times the concentration of holes, using the value of mobility of hole of silicon and concentration of hole at 300 Kelvin. We obtain that the component of conductivity due to hole becomes equal to 72.5 micro Siemens per meter. In part B we have asked to evaluate the component of conductivity due to electrons. So we have given these numerical values, that is the concentration of electron, mobility of electron in silicon at 300 Kelvin, and we know that the mobility the conductivity of electron is equal to minus mu e rho e. Remember that the mobility by definition is positive, but the charge concentration is negative. So multiply these two values, which result in 348 micro Siemens per meter, and the combine and the conductivity of silicon then equal to the sum of conductivity due to hole and due to electron. Add these two components, you will get the total value of conductivity of silicon at 300 Kelvin. Now let us discuss that what is dielectric material. Dielectric material basically comprises of bound charges. There is no free charge, especially in perfect dielectric there exists no free charge. All the charges are bounded, and the basic particle of fundamental particle of dielectric material is electric dipole, which is given by this relation. P represent the dipole, Q represent the magnitude of the charge, D represent the separation between the positive negative charge, which directed from negative charge towards positive charge. The unit of dipole moment is coulomb meter. When the sample of dielectric material is placed in an electrostatic field, as shown in the left side or on the right side, so all the charges are aligned, that is, the dipoles are aligned in the direction of applied electric field. The cumulative response of the dipoles inside the dielectric material per unit volume represent the polarization. So in the dielectric material we have no free charge, and we know the relation of Gauss's law for the free charges. So the question is how to define the Gauss's law in terms of free charges in dielectric material, and how to modify the D field in dielectric material other than free space. So for this purpose, let's just consider a dielectric space. As we have discussed that dielectric material actually contain bounded charges, there exists no free charge. Inside this dielectric space, let us consider an incremental volume having closed surface S. Let the top surface, the elemental surface, is denoted by delta S. In the presence of applied electric field, there produce polarization effect. Polarization means dipole per unit volume. Suppose there are n dipoles per cubic meter. N polarization. N represent polarization. Dipole per cubic meter represent polarization. So if we are dealing with the incremental volume delta V, then the total dipole moment is obtained by the vector sum of all electric dipoles, that is from I equal to 1 to n time delta V. The unit of electric dipole is coulomb meter. The electric polarization, that is the net effect of all those dipoles in a sample of dielectric material, is known as polarization, or this is also known as density of electric dipole, and is given by equation number 2, that is dipole per unit volume when the volume shrink to 0. Shrink to 0 means when the whole sample is occupied by the electric dipole, then that effect represent the electric polarization, and all the charges in the electric dipoles are aligned in the direction of applied electric field. In the absence of electric field, polarization is nearly equal to 0. There are some electric material in which dipole already does exist, but they are oriented randomly, so the net effect of those dipoles is 0, hence polarization is 0. But when electric field is applied to that sample, so then all the dipole moment are aligned in the direction of applied electric field. In order to modify D field and hence modify the Gauss's law for free charges, let us consider an elemental surface of the closed surface. So initially let us consider that we have a positive charge which is located above the elemental surface of the closed surface. When we apply the electric field, so the positive charge cover a distance 1 upon 2d cosine theta in vertical direction, that is parallel to the normal to the surface. Similarly, when initially in the absence of applied electric field, when there is a negative charge just below the elemental surface, then when apply the electric field, so it cover a distance 1 upon 2d cosine theta in vertical direction below the incremental surface. So for instance, we have n molecule per cubic meter. Then now we are going to define the bound charges. So the polarization basically makes an angle theta with respect to the incremental surface or elemental surface of closed surface. So the incremental bound charges bound by the surface above or below, so that is equal to nqd cosine theta, the magnitude of that incremental surface, or one can write the above relation in vector form, that is the product of nqd factor. This one represent the polarization because n represent the molecule per cubic meter, qd represent the dipole moment, delta s the incremental surface area, vector area. So in order to define the total bound charges inside this closed surface, we have to apply the surface integration. So the surface integration then becomes equal to surface integration, P represent polarization, which is equal to nqd. The unit of polarization is coulomb per square meter. Equation number 3 define the total number of bound charges inside the closed surface, and those left outside this closed surface now behave like free charges. So the total charge in this dielectric space becomes equal to the sum of the bound charges plus free charges, and the total charge is equal to, in term of Gauss's law, equal to surface integration epsilon naught E dot ds. Actually we are comparing the free charges effect with the free space effect, with the charge in the free space. So rearrange equation number 4, and using the bound charge relation we obtained this relation, and hence this one, that is q sub f represent free charges, that is total number of free charges bounded by enclosed by the dielectric space, which is equal to the surface integration of d field in the dielectric material dot ds incremental surface area. So this is exactly similar, this relation now exactly similar to the relation of Gauss's law for free space, and we have obtained the Gauss's law relation for free charges in dielectric material, where d is equal to, now d is also modified because of polarization effect, so d is equal to epsilon naught E plus P. Capital P represent the electric polarization. Electric polarization means dipole per unit volume. This also represent the dipole moment density, and its unit is coulomb per square meter. Now, what is polarization in terms of electric field? When we apply the electric field to any dielectric material, so there is a direct relationship between polarization and the electric field. The constant of proportionality is given by a chi sub e, epsilon naught. Epsilon naught represent the permittivity of free space, and chi e represent the susceptibility of dielectric material. This is dimensionless quantity, and what do we mean by susceptibility? For instance, the human blood pressure is susceptible to salt. When we take a little amount of salt, so that actually directly affect the blood pressure of human beings, or our blood pressure. So this means that the human blood pressure is susceptible to the salt. Similarly, when we apply the electric field, so then how much the material is affected by the applied field, that we measure using how much the material is susceptible, means how much field can passes through the sample of dielectric material. So how much the material is susceptible to the applied field. So polarization is given by this relation chi sub e. Chi e represent the susceptibility, which is dimensionless quantity, times e. Now plugging the expression of polarization in the modified form of electric flux density, so we obtain this relation, that is D is equal to epsilon naught times epsilon r E, where epsilon r represent the relative permittivity or dielectric constant, and this relative permittivity or dielectric constant is equal to 1 plus chi e. Hence we modify the Gauss's law for dielectric material. And why? Because in dielectric material we have no free charge. There is actually exist bound charges. So in this discussion we define the Gauss's law in terms of free charges of dielectric material, and we have also modified the D field for dielectric material, which is equal to epsilon times E. Epsilon in this case equal to epsilon naught times epsilon r, where epsilon r represent the relative permittivity. In the modification of D field and hence the Gauss's law, we obtain these three important relations in integral form, where rho t represent the charge density of total charge, of bound charge and free charges. Rho b represent the density of bound charges, and rho v actually represent the density of free charges in a closed surface. So these three relations are in integral form. So how to convert these integral form to differential form, so that we can achieve using divergence theorem. According to divergence theorem, we can replace the surface integration of any field by the divergence, by the volume integration of the divergence of that field. So using divergence theorem, we have defined, or we can obtain these three differential form of the above integral form relation, that is a prime, b prime, and c prime, that is delta del dot epsilon naught E represent divergence of electric field of total charge density at a single point. Similarly, del dot P polarization is equal to minus rho B. Negative value represent the number of the increasing number of bound charges in closed surface. But if you look at the differential relation part C, or number C, so this is exactly similar to the previous relation of Gauss's law in differential form for free charges. So the D field is still related to free charges. D dot D is equal to rho V. So in dielectric material, charges are bounded, there is no free charge. That is when we deal with perfect dielectric material. So in perfect dielectric material, conductivity is nearly equal to 0, or exactly equal to 0. So there exists no free charge. But when we deal with the dielectric material, and if the dielectric material is lossy, then there exists free charges. Remember this thing, that is we call those materials as lossy dielectric material. But we have obtained the exact relation of the Maxwell equation as for dielectric material as we have obtained for the charges in D field in a free space. Let us try drill problem D 5.8 on page 133. In D 5.8 we have given a slab of dielectric material has a relative dielectric constant, that is epsilon r equal to 3.8, and contain uniform electric flux density D field at nanocoulomb per square meter. Now we have given that, let us suppose that the material is lossless, that is conductivity is 0, there exists no free charge. Then find the value of E, magnitude of E field, and the magnitude of polarization. In part C we have asked to find the average number of dipoles per cubic meter if the average dipole moment is 10 power minus 29 coulomb meter. So part A, this is given data, that is epsilon r equal to 3.8, the magnitude of D field is 8 nanocoulomb per square meter. So D field is equal to epsilon times E, where epsilon is basically equal to the product of epsilon naught times epsilon r. So E field then becomes equal to electric flux density magnitude divided by epsilon naught epsilon r. Plug in the values of D field and epsilon naught epsilon r, so we come across this value of the electric field, which is exactly matched with the answer given in the book. How to obtain the magnitude of polarization? So we know that epsilon r is basically equal to 1 plus chi e. Susceptibility, so susceptibility becomes equal to epsilon r minus 1, and chi e is equal to 3.8 minus 1, which is equal to 2.8. As we know that the polarization is given by this relation. Plug in these values. We also know what is the electric field which we have obtained in part A. So insert the numerical values of each factor in this relation. We come across this value of the magnitude of polarization, which is equal to 5.9 nanocoulomb per square meter. Now we have asked to find the average number of dipoles per cubic meter. We have given the average dipole moment, that is 10 power minus 29 coulomb meter, and the dipole per cubic meter, the average value of dipole per cubic meter becomes equal to polarization magnitude divided by the average value of dipole moment, which result in 5.9 into 10 power 20 per cubic meter. Now let us develop the boundary conditions for dielectric material, and in this case we are going to consider perfect dielectric material. The procedure is similar to the procedure as we had used in obtaining or defining the boundary condition for interface between free space and a conductor. So let us consider a boundary which is represented by a red line between two different dielectric materials, material 1 and material 2. The permittivity of material 1 is different than the permittivity of material 2. So we are going, first let us define the tangential boundary condition at the interface between two different mediums. When electric field or D field incident on the interface between two different materials, so the electric field split into two components at the interface, that is tangential component and normal component. Now the question is how to obtain the tangential component of electric field and normal component of electric field. So for that purpose, let us consider a closed path A, B, C, D, A. The length of this rectangular path is delta W, and the width of this incremental path is delta H. We have to obtain the relation for tangential component of electric field in medium 1 and medium 2. So we know that in any conservative field, the total work done around any closed path is always equal to 0. So in along this contour or rectangular path, we can split the left side of this relation into 4 integration. That is integration from path A to B, from path B to C, from point B to C along this path, and integration along C to D, and integration along D to A. In order to achieve the tangential component of electric field in medium 1 and medium 2, we must move very close to the interface. So for that purpose we use this approximation, that when delta H tend to 0, so the contribution due to path B to C and path D to A becomes vanish. So we left only two paths, one in material 1 and another in material 2, that is AB path and CD path. So the contribution due to integration along B to C and D to A vanish. So this expression take this form. Now the integration from path from point A to B is equal to E tangential 1 delta W, as the two paths in material 1 and material 2 are opposite to each other. So plus E tangential 2 become the tangential component of electric field in material 2 is multiplied by minus value of delta W, which result in this relation. That is, the tangential component of electric field across the boundary are continuous. That is, the value of electric field, the tangential component of electric field above the interface and below the interface has same value. There is no change in the values of electric field component along tangential component across the boundary. This is the representation of tangential boundary condition in scalar form. In vector form, you can write the above equation in this form, where n represent normal to the interface, cross E1 total electric field in material 1 minus total electric field in material 2 is equal to 0 at the boundary. These two relations represent the tangential boundary conditions, that is how to obtain the tangential component of electric field at a interface between two dielectric materials. Now let us the tangential component of D field can be achieved by dividing and multiply the left side and right side of this relation by epsilon 1 divided by epsilon 1, epsilon 2 divided by epsilon 2. So the above factor represent D tangential 1, and the product of epsilon 2 with E tangential 2 represent D tangential 2. So this means that the tangential component of D field at the interface between two different dielectric material are discontinuous by the ratio between the permittivity of material 1 and permittivity of material 2. That is, the tangential component of D field are components of D field are discontinuous by this ratio, whereas the tangential component of E field are continuous across the boundary. There is no change in the tangential component of E field across the boundary between two different dielectric material. Now let us develop the relation expression for normal boundary conditions. For normal boundary conditions, we actually use the integral form of Gauss's law. And let us consider an interface between two different dielectric material. The red line represent interface or boundary between M1 and M2. The conductivity of material 1 is 0 and that of material 2 is also 0. So the two material are perfect dielectric material. Epsilon 1 represent the permittivity of material 1 and epsilon 2 represent the permittivity of material 2. Let us consider a capsule-like shape, a cylindrical shape at the interface between two different mediums. The cross-section area of the cylindrical shape in material 1 is delta S1 and that in material 2 is delta S2. The cylindrical surface of this capsule-like shape is delta S3. The length of the cylindrical shape is delta H. So we can split the left side of this relation into three parts. That is the surface integration over the cross sectional area of cylinder and material 1 and material 2, and the integration over the cylindrical surface. But we are actually interested in the field component at the interface. So for that purpose we actually use the uh, the uh, we want to let delta H tend to 0. So using this approximation, the volume vanish. Hence the contribution due to cylindrical surface becomes vanish. That is, this one become equal to 0. And we have left two discs, that is the cross sectional areas of the capsule like shape in material 1 and material 2. So but remember that in this case the vector area of cylindrical the disk in material 1 is in upward direction, and that in the material 2 is in a downward direction. Both are in the opposite direction but having same magnitude. So for delta H, as I have already told you that the contribution due to the cylindrical surface becomes equal to 0. So we left this relation, and remember that the volume charge density reduced to surface charge density. For example, let's assume there are some free charges at the interface. Then in that case the volume charge density reduced to surface charge density. So let us evaluate this integration over the cross sectional area of cylindrical shape in material 1, which result in dN1 delta S, as we know that the D field from any charge in electrostatic case is in normal direction. So D sub N1 delta S1, which is the value of this integration, plus D sub N2, which is the value of times minus delta S1. As I told you that the magnitude of delta S1 and delta S2 is the same, but they are directed in opposite direction. So that why we place a negative sign in this term. And the surface integration, the surface charge density, the total charge over the disk in material 1 is equal to rho s time delta S1. So cancel the delta S1 on both sides. So we obtain this relation. This represents the normal boundary condition of normal component of D field at the interface between two different dielectric material. If there is some free charges at the boundary, then these two components are discontinuous by that surface charge density. This is the representation of normal boundary condition of D field at interface between two different dielectric material in scalar form. In vector form, you can also write this one in this form, that is n cap represent unit normal, n cap dot d1 field in total d1 field in medium 1 minus d2 field in medium 2 is equal to rho s. This is in vector form. Now let us see these two relations for perfect electric dielectric material. So in perfect electric dielectric material, the conductivity value is 0, so the surface charge density is 0. Hence this relation reduce to this form, and this one reduced to this form. So these two relation represent the normal boundary condition at the interface between two different dielectric material. Now let us check the obtain the relation for normal component of E field in material 1 and material 2 at the interface between these two material. So the normal component of E field at the interface between two different dielectric material are discontinuous by the ratio between the permittivity of material 2 and permittivity of material 1. Now let us try an example. In this example, we have given an interface between two different dielectric material. That is, the permittivity of material above the the green line is epsilon 1. This represent material 1, and the permittivity of the material below the green line is denoted by epsilon 2, and also consider that epsilon 1 is greater than epsilon 2. So look at the figure. In the figure, the theta 1 is greater than theta 2. Why? Because epsilon 1 is greater than epsilon 2. That is, D field move away from the normal to the interface, and in material 2 the D field is moving towards the normal to the interface. Okay, so D split into two components, that is D and D2 field split into two components at the interface, that is Dn2 and dt2. Similarly, total D field represented by a red line, a red arrow. So this D1 field also split into two components, Dn1 and dt1. So using the figure, we obtain Dn1 is equal to D1. The magnitude of D1 field in medium 1 cosine theta, this one time this, also equal to D2 time cosine theta 2. So we know that the normal boundary condition of D field and at an interface between two different dielectric material are continuous. So using that boundary condition, we obtain this one. And as we know that the tangential components of E field across the boundary is components are continuous. So using the tangential boundary condition of dielectric material, multiply and divide the left side of this relation by epsilon 1, and multiply and divide the right side of this relation by epsilon 2. So we obtain D101, which is equal to epsilon 1 divided by epsilon 2, D102. D102 means the tangential component of D field in material 2 and the tangential component of D field in material 1. Divide D101 by D102. So look at the figure. D tangential 1 is basically equal to this line is parallel to the boundary, and theta 1 is in front of the this line, so this actually make a triangle. Consider this triangle. So d10 1 equal to total d1 field magnitude times sine theta. Similarly, consider this triangle, this one. So d sub t2 divided by d2 magnitude is equal to sine theta. So replace divide this by d10 1 by d10 2, which is equal to d1 sine theta 1 divided by d2 sine theta 2, and these two components, as I told you, that d10 1 divided by d10 2 are discontinuous by the ratio between epsilon 1 to epsilon 2, that is the permittivity of material 1 and permittivity of material 2. So let us determine the magnitude of d field in material 2 in term of d1. So d2 field is basically, the magnitude of d2 field is equal to square root the square of the d tangential component 2 square plus the normal component of d2 field square. So using this relation, this one, that is d10 2, the tangential component of d2 field is equal to epsilon 2 divided by epsilon 1 d10 1, and we know that the value of from the figure you can obtain d10 1 is equal to the magnitude of d1 times sine theta. So this d10 2 becomes equal to epsilon 2 divided by epsilon 1 d1 sine theta 1, and we know what is d10 d sub, that is the normal component of d2 field, which is exactly equal to d1 cosine theta 1. So plug in the value of d10 2 in term of d1, and the value of d, or the expression of dn2 in term of d1. Rearrange this one. Finally we obtain the magnitude of d2 field in term of d1. Similarly, rearrange this relation for the magnitude of E2 field. So eventually we come across this relation. Now look at this one. In this case, as we know that epsilon 1 is greater than epsilon 2, so this means that in material 1 the value of d1 field is greater than the magnitude value of d2. But if you look at the E2 magnitude, so in this case epsilon 1 is divided by epsilon 2, that is a large value is divided by small value. So this means that the value of E2 magnitude is greater than epsilon E1 in material 2. This is the conclusion. That is how to apply the boundary condition to an interface between two different dielectric material for any given problem. Okay. Now let us apply the preceding theory to a drill problem D5.9. In this problem we have given two region. Region 1, which is located in Z is less than 0 region, and this region is occupied by uniform dielectric material having relative permittivity 3.2. Region 2, which is denoted by another half space, Z is greater than 0 region, and the material in this region is characterized by relative permittivity having value 2. and in this problem we have given the one field. We have asked to find the normal component of this one, the tangential component of this field, the magnitude of the tangential component of this field, the magnitude of d1 field, theta 1. Theta is actually the angle between d field and normal to the interface, and the polarization. So the step by step solution to this problem is given on slide number 20. This is drill problem D 5.9, page 137. This is the given field. The figure reflects the given problem. Z is greater than 0 region is occupied by region 2. The relative permittivity of material 2 is 2, and Z is less than 0 region or half space is occupied by another dielectric material having the relative permittivity of this material is 3.2. So according we have asked to find the normal component of the given field, which we can in this case look at. This is an interface Z equal to 0 plane, which is XY plane. This plane actually represents interface between two different dielectric material. So normal to this interface is directed along z-axis, which is AZ unit vector. So dn1 represent the normal component of the given field in region 1. So this is equal to AZ dot d1 total flux density in material 1, total electric flux density in material 1. So at z equal to 0 plane at interface, d1 becomes, look at az dot ax equal to 0, az dot ay unit vector equal to 0, az unit vector dot az unit vector become equal to 1. So d in 1 becomes equal to 70 nano coulomb per square meter. Now we have asked to find the vector tangential component of the given d1 field. So we have to apply this boundary condition at z equal to 0. That is to take the cross product of AZ unit vector. AZ unit vector represent unit normal to the interface between region 1 and region 2 at z equal to 0 plane. This is normal to the interface. So AZ unit vector cross d1 define the vector tangential component of d1 field. So AZ cross AX, that is AZ cross AX equal to AY. AZ cross AY equal to minus, use this procedure, right hand procedure for unit vector vector triplet product. So AZ cross AY equal to minus AX unit vector, because this product is carried out in the clockwise direction. Okay, and AZ cross AZ unit vector equal to 0. So we obtain the component of tangential component of d1 field in vector form equal to minus 30 AY unit vector minus 50 AX unit vector and 0 component along z direction, because the cross product of AZ unit vector with AZ unit vector equal to 0 and nano coulomb per square meter. Then how to obtain the magnitude of tangential component of d1 field? So that is straightforward. Just take the apply the distance relation. So we obtain the magnitude of the tangential component of d field, which is 58.3 nanocoulomb per square meter. In part D, we have asked to obtain the magnitude numerical value of D1, magnitude of D1. So that is straightforward. Use this relation, and the numerical simplification gave us 91.1 nanocoulomb per square meter. Now we are going to define theta 1. This is the angle between the one field and the unit normal. As I told you, in this case the unit normal is directed along z-axis, which is az unit vector. So az, that is to define the projection of d1 in the direction of az unit vector. So az dot d1 is equal to az magnitude times d1 magnitude cosine theta 1. Simplify this one. So finally we obtained 39.8 degree. This is the angle between d1 field and the unit normal to the interface. The polarization relation is given by this one. So that is epsilon naught times chi E1. Chi E1 represent the susceptibility of material 1. So hence from the given D1 field we can easily define E1 field, which is given by this relation, and divide the 1 by the dielectric constant of material 1, so which result in this expression, nano volt per meter, as epsilon r1 is equal to 1 plus chi E1. Chi E1 represent the susceptibility of material 1. So susceptibility of material 1 becomes equal to epsilon r1 minus 1, which is 2.2. Remember that the susceptibility is dimensionless quantity. So plug in all these informations and this expression. Finally we came across this vector. This vector represents the polarization vector of given D1 field in material 1, minus 20.57 a x unit vector plus 34.375 a y unit vector plus 48.125 a z unit vector nanocoulomb per square meter. And the end of the lecture. If you have any problem in watching this video lecture, you can send us email, or you can place a message on MS Team. We will have a session in next week on this lecture. So in this lecture we have actually discussed the image theory, how to use the concept of image theory to any chart configuration located at above the conducting sheet. Then we have discussed the semiconductors. Then we have discussed the dielectric material, the nature of dielectric material, and we have also discussed the tangential boundary condition, how to use the boundary condition. For that purpose I show you two different problems, one an example which is given in the book, and second I have solved the drill problem given in the book. Thank you.